Okay, radio signals and waves. So your basic radio station, you've got a transmitter, you have a receiver, and you have a switch in the middle. And then you have a power supply running it. And what's that thing up there? Oh, it says it's an antenna, and you got the feed line. In the old days, you transmitted by throwing the switch to one side, and you transmitted, and you said over, and turned it over to the receive side. You had to manually do that. Now we've got automatic. You push the button on modern equipment. Do we have any modern equipment you have to flip it back and forth?
So I started out with a separate receiver transmitter pair. I used a relay. So that was keyed to the microphone. And when I keyed the mic, the relay would throw, and it would go from receive to transmit. And it would block the transmit from overriding the receiver. So the receiver was already shunted to ground when the transmit came on.
So,
otherwise you'd blow the receiver up.
Right, so this receiver is looking for millionths and billionths of a volt coming in, and then it jacks up the voltage so it can make an audio signal. Well, this thing's sending out lots and lots of watts. And it's going out the same feed line, and so if they're connected, you blow out the, let's see,
even
the
if it's
receiver.
not connected, just because they're next to each other.
Oh, even that. Okay.
So you'd have to ground the receiver when the transmitter was on.
Yeah, so like with a repeater, we've got, they're filters. We call them cans, but you're receiving a signal and you're transmitting a signal at the same time. And so we've got a system in there to separate those signals so you don't blow things up. In the old days, you literally threw a switch when you wanted to change it. Now you just let off of the button and it does it for you on everything I know about. Okay, what happens during radio communication? You're transmitting or sending a signal. The information, voice data, video commands, etc. is converted to an electronic form. The information in electronic form is attached or embedded on a radio wave, which is called a carrier. Remember, yellow is on the test. The radio wave is sent out from the station's antenna into space. Hopefully it doesn't keep going into space. On the receiving end, the radio wave, the carrier, is, with the information, is intercepted by the receiving station's antenna, and it's bits at tiniest little fractions of volts, of power. The receiver extracts the information from the carrier wave. The information is then presented to the user in a format that can be understood, whether it's a sound, pictures, words, a computer screen, or a response to a command. So we can do all kinds of things. So when you're flying a remote-controlled aircraft or driving a remote-controlled car, you're sending a signal to it. It's receiving it. It may even be sending its data back. Well, it sounds pretty simple, right? Just send a little electronic signal out there. But in reality, it's pretty complex. Complexity is one thing that makes radio fun. I don't know about that. I thought the part that made it fun was actually making the communications, not the complexity of doing it. Don't be intimidated. You'll only be required to know the basics, but you can learn as much about the art and science as you want. You can build your own radio. I think I mentioned it, the Heil Pine Board radio is still available out there. Radio, oh, here you've got some yellow. Radio waves have electric and magnetic fields, or electromagnetic radiation, and are AC, alternating current. So RF, radio frequency, is AC. The electric and magnetic fields of an electromagnetic wave are at right angles to each other. So you got the electric field and the magnetic field. And that's what makes up polarization. Now, radio waves are used to carry the information you want to convey to someone else. And the velocity of a radio wave traveling through free space is the speed of light 3 times 10 to the 8th.
That 300 million meters per second, that's in a vacuum.
Yes, it's not in a
when
piece.
When you're in air or another medium, it is slower than that. And that has a direct relation to how radio waves get bent.
It also has a relationship to how long your antenna is, because copper is a medium that is not a vacuum, right? So we convert 468, we'll get to it, but 468 for a half wave, or twice that for a full wave, gives you the actual length of the wire you need. And we always go with a half wave dipole, so it's 468 divided by the frequency in megahertz. And that is compensating for the velocity factor in the copper wire. And it's different for stainless steel or aluminum or copper. but they're all close enough that you can just use 468 and you'll be close. And you always cut your wire what? Short or long? Long. Because it's real hard to, you can stretch them, but they didn't break.
I wonder if elevation affects that, like elevation affects.
I'm sure it does because
Yeah.
the density of the atmosphere is less.
Okay, that's right.
So when I get up to 12,500 feet in my Cessna, with the throttle at the firewall, I got 45 to 50% of my power available because there's just not enough air. Okay, wave vocabulary. Before we study radio waves, you need to learn some wave vocabulary. The amplitude is from here to there. How high and low it goes. That's amplitude. The frequency is the distance from there to there. Okay, in meters, we also call it a wavelength in meters as well. The period and the wavelength is from there to there as well. And harmonics, okay. The third harmonic, your antenna is resonant at a set frequency. At the third harmonic,
Multiple.
it will also be resonant. So a 7-meter antenna would be resonant at the third 3 times at 21.
Means 7 megahertz.
7 megahertz, I'm sorry, 7 megahertz, which is 40 meters. I'm also going to be able to use that antenna at 21 megahertz 3 times, the third harmonic. But I can't use it at 14. It's not going to be resonant. And it will be at the odd harmonic, the third, the fifth.
Every odd harmonic.
It's odd. So third, fifth, seventh, ninth, all of those, it'll be resonant. It may not be effective, but it is a harmonic of, but it's not yellow.
So Bruce,
Yes, ma'am.
why do we care? What does it do?
So when I put up a 40 meter, a 7 megahertz or 40 meter antenna, dipole, I can also use it on the 21 megahertz band,
So you can make a multiple band antenna by choosing the right
the right length.
length for the antenna.
When you say you're making an antenna, like, you're building it specifically for certain
Frequencies, yeah.
frequencies, so there's not a like one antenna fits all.
Yeah, there are.
Every-
but there's compromises. Remember, there's no free lunch.
Yeah, every antenna is a compromise. So,
So it'll work, just not as good. Or,
well, there's that, or it might not work at all if you're way off. So that's the antenna. The old one didn't look like this. Then the Baofeng said, we're going to put a better antenna on there because we're getting a bad rep. Although I don't know how bad it can be. And then you buy this one. Well, this is longer. It's less compressed. This has got the same amount of length of wire in it, but it's coiled. This one's longer, so it's got exposure to more stuff. This one works better. Same thing with your antennas. You're always looking for a compromise that does what you want to do. So we have a whole section on antennas and feed lines.
And you will struggle with this for a while.
It'll be,
You just gotta try it.
none of that's yellow though. Where am I on the radio dial? There's 3 things you must tell someone when identifying where to meet you on the radio dial. The radio frequency or spectrum, where you're at 2 meters or 440 or whatever. The band, the frequency, the specific frequency. The time, kind of important. Fridays at 8 o'clock, Aegon on the Peak Radio Association. Come say hi. Have a backup plan, a second option, just in case the frequency's occupied, or in case of HF, the band's not open.
Our repeater's down.
Or the repeater's down. So the Care Club has a backup repeater that everybody knows to go to. RF refers to radio frequency signals of all types.
Those are electromagnetic frequencies. You can have the same frequency in audio, but it's not RF. I just want to make that differentiation. You can have the same frequency.
Right.
One's RF, one's audio, 2 different animals, same frequency.
You can even have the same frequency in vibrations
Yeah.
inside a physical piece of material. Frequency doesn't mean radio frequency, but radio frequency or RF is radio frequency. The RF spectrum is the range of wave frequencies which will leave an antenna and travel through space. The RF spectrum is divided into segments of frequencies that basically have unique behaviors that are, this band has the same behaviors all the way through it. So that's what we call 20 meters, 40 meters, 80 meters, 60 meters. 120 meters, 2 meters, VHF, UHF, all the different bands. Okay, remember that little sign up there? Somebody remembers. Good job. Lambda. Lambda is a symbol for wavelength. C is the constant, which is the speed of light, 300 million meters per second, or 3 times 10 to the 8th. F is the frequency in megahertz, and that's just to define it, and the formula is there. It's just 300 divided by the frequency in megahertz. So this is the radio frequency spectrum. So it's kind of weird, because you have high frequency, and then you go down, you got medium frequency, low frequency, very low frequency. Well, that's not all that high, because now we got very high and ultra high, and then, what's
Super
that?
high.
Super high and extremely high, or something. Okay? Well, why didn't we have this one over here? Anybody guess? Because back in the dark ages, they thought that was high, and then they figured out how to make it higher. So that's why it's spread out like that. Show of hands, who's heard the name Nikola Tesla? Nikola Tesla. I don't see a hand up.
Well, say, what do you want to know about him?
Well, what do I want to know about it? I want to know how he was going to get the free electricity out of the air.
Oh, we're just going to send electrical bolts.
Well, it's
across
here
the
already.
country.
You could turn on your AM radio or your FM radio or any radio and hear a signal. That is electromagnetic radiation that is in the space you're in. So right in this room right now, if I turn on one of those ham radios, I can listen to any of the frequencies that somebody's transmitting on. There's electromagnetic radiation in this room. That's energy that you could collect. That was kind of his theories. It's billions, I think it is, of a volt, is a readable signal. We're being irradiated, man. If we can hear that, we're being irradiated. But we already covered that that's non-ionizing, so it's not hazardous, right?
Are there places where there aren't any?
Probably Antarctica. It's still there, but it's probably super weak. Inside of a Faraday cage, it's a proper Faraday cage. So anyway, this is the spectrum. We've got very low frequency all the way up to EHF. VHF, frequency range of 30 to, oh yeah, this is on the test, 30 to 300 megahertz is VHF, 30 to 300 VHF in megahertz. Frequency range 300 to 3000 is UHF, so it's very high and ultra high. 30 to 300, 300 to 3000. So it's a bunch of threes, it's just how many zeros. VHF has fewer zeros than UHF. So where am I? Back to how to tell where you are in the spectrum. Bands identify the segment of the spectrum. Everybody's got a band plan there. It tells you all the different frequencies that amateurs have. Well, most of all of them. All the ones that we use a lot. There's more of them at the higher frequencies that we do have the ability to use. The bands identify the segment of the spectrum where you will operate. So each one of those little color blocks is a band. And the colors that are there go with the key on the right-hand side and tell you what license is required to do that kind of transmission. So the little squiggly line on the far left of most of them is CW and data. The green is phone and image, so you can send TV signals out on the green set blocks. The red is RIDI and data, so you can do FT8 or whatever, or RIDI. Orange is fixed digital message forwarding system, so probably like WinLink. And then there's different rows in each one of them, and that's based on your level of license. N is novice. We don't issue those anymore, but there still are novices out there. T is tech, G is general, A is advanced. They don't issue those anymore, but that's one step below extra. There's not a lot of advanced, but they are out there. That's it for your licensures. And then it's just a little color code thing. I still have one of these posted right in front of my radios. And I refer to it all the time. So the bands identify the segment of the spectrum where you're going to be operating. The wavelength is used to identify the band. Frequencies identify specifically where within the band that you are. So 2 meters is a band from 145 to 148. So that tells you specifically where you are in that band. Okay? As the wavelength gets shorter, the frequency increases. This is confusing to people. It confused me for the longest time. I mean, I could think about it and get it straight. But to just automatically go there. 160 meters is 1.8 megahertz. The longest wavelength on that chart is 1.8 megahertz, really long.
In auditory, if you have a wind chime and you've got a short wind chime, you get a high frequency. You hit it high note. A long wind chime, you get a low note. So the longer that wavelength, the lower tone. And it's the same thing with antennas. You have a longer wavelength and a longer antenna, you'll have a lower frequency.
What's that?
Like a guitar string, you play notes,
Yep,
and it
yep.
vibrates differently.
Right. Right. So, okay, so the wavelength gets shorter, the frequency increases. So as I go from 160, is 1.8 megahertz, I get to 2 meters. Okay, 160 is 160 meters. If I get down to 2 meters, it's 147 megahertz. It's a higher frequency and a shorter wavelength. In addition to frequency, the approximate wavelength in meters is used to identify amateur bands. So if you look on your chart there, you've got 2 meters, you've got 70 centimeter band. That's what we call the band by the approximate frequency. For the station antenna to efficiently send the radio wave out into space, the antenna must be designed for the specific operating frequency. So you design it for the specific one you want to use. The antenna length needs to closely match the wavelength of the frequency to be used. So any mismatch between the antenna length and the frequency wavelength will result in radio frequency energy being reflected back to the transmitter, which is your scanning wave ratio or SWR, and not being emitted in space. Well, that's not efficient, right? So you want that antenna to be, where do I want to work the most? That's where I want it. When we imprint information on the radio wave, we modulate the wave. That's the data, it's the modulation. Turn the wave on and off is CW or Morse code, constant wave or Morse code. We can use voice in AM, which is amplitude modulation, or FM, which is frequency modulation. So we can vary the amplitude of the signal or the frequency of the signal. We can code the information and modulate it. Data is RTTY, which is radio teletype. PSK31, I don't remember what it stands for. FT8, that should say zombie mode, not FT8. You click CQ and you walk away, go to the restroom, and get a cup of coffee, you come back, oh, hey, I've got a contact gun. So I call it zombie mode. But, hey, you can get some stuff. The different modulation techniques are called modes. So we have AM, FM, AM subdivided, AM, upper side band, lower side band, different modes in the radio. And that's the type of modulation we're putting to the signal. Changing a signal in some manner to convey information is modulation. Notice there's no yellow yet. You can change the amplitude, you can change the frequency, and you can change the phase. So AM, amplitude, FM, frequency, PM is phase modulation. All methods of modulation. I think all three of those could be on the chest.
Yeah.
Signal with no information is unmodulated. Did we cover what an unmodulated carrier is? Unmodulated is 1. That's the only thing you gotta remember. Unmodulated in the question is 1. Changing a signal in some manner to convey information, you can do it analog, voice or phone. The information is the voice. You can do it digitally. The data mode or digital mode. The information is the data. And also on digital, we now have a radio that will take your analog signal going into the microphone, goes into the computer, into the radio, which is really a computer now, and is turned into digital information, spit out on the antenna. The other receiver picks it up, brings in the digital information, converts it to analog, and spits it out on a speaker to you. And it's light years ahead of.
And you can tell the difference if you hear it.
If you hear digital, it's crystal clear, but it takes out all the noise. Okay, continuous wave, CW is Morse code. It's in yellow. CW is Morse code for continuous wave. Signal at one frequency whose amplitude never varies. Normally used to refer to turning the signal on and off in a specific pattern to convey information. Dit, 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 dot, 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 dit, dit, dit. It's either SOS or OSO. Continuous wave, Morse code. So you've got this signal here. This is your carrier, and then you turn it off. And it's back on, you turn it off. Continuous wave is Morse code, that's all you need to know off that slide. Amplitude modulated modes, amplitude modulation is AM. Carrier plus 2 sidebands. You got the carrier going right down the middle, and you got 2 sidebands. Gives you higher fidelity, there we go. Single sideband, carrier and 1 sideband are suppressed. So AM is a carrier, and then 2 sidebands. Sideband is we suppress the carrier and 1 side or the other, because these are mirrors, the mirrors of each other. And so a radio can just create a mirror image and inject the carrier. The advantage is we get more power efficiency. Remember this term, the envelope is the waveform created by connecting the peak values of the modulated signal. This is the envelope. See, that looks a little short to me. And the peak to the peak is the envelope. Sound waves that make up your voice are a complex mixture of multiple frequencies. This complex mixture is embedded on a carrier. The 2 sidebands are created that are mirror images, these 2 little bumps. And there's a drawing of it. So we have the carrier and sidebands. One upper and lower, or upper and lower. We have the carrier, the lower sideband, and upper sideband. Voice bandwidth is 300 hertz to 3 kilohertz. That's how wide the signal is. And the AM bandwidth is twice the voice bandwidth because you got two sides to it. Okay, so characteristics, you got the carrier in the center, the lower sideband, the upper sideband, and amplitude modulated AM modes and lower sideband. Only the lower sideband is transmitted. Upper sideband, only the upper sideband is transmitted. It's got higher efficiency and it uses less bandwidth, so we can send more stations into a given space on frequency on the band. Okay, it's got higher efficiency, less bandwidth. So single sideband modulation, or single SSB. A single voice is made up of identical mirror image sidebands. We can improve efficiency of the transmission by transmitting only 1 sideband and then reconstruct the missing sideband at the receiver. So we just have a carrier and a sideband, and the one that would be over here is just this flipped over. And so the radio can go like, well, let's just create that in reverse. And so it can inject it over here, and it can inject the carrier. So why send all that? Why spend all that electricity and energy? Why not stuff all that energy into this, just the sideband? And that's what sideband does. Sideband is transmitting only 1 sideband. AM modes, single sideband is often used for long distance, weak signal. It's used for long distance, period. And there's a lot of guys that are using 2 meter, which is line of sight, right? That are doing 2 meter sideband because you can reach Roseburg even from here. But you can't do that on FM. But on AM sideband, you can. Sometimes. I haven't figured out how to do it yet, but I don't have a beam pointing that way either. So single sideband is often used for long distance weak signal contacts on the VHF and UHF bands. Okay. FM modulated modes. Frequency modulation is FM. Deviation is the amount of frequency change. So you change the frequency, let's say it's 147, and then you change to 147 point something, 0.001, and down to 146.999. Vary the frequency. I don't know how much it varies, but that's how you change the frequency instantaneously as you're speaking or sending the data in. Phase modulation is a constant power, whether it's modulated or not.
That's true of FM as well.
Yeah. Now, when you go to AM, when you go to tune your radio, because half of you at least are going to get your Gemma licenses. You go to tune your radio on AM or single sideband, you step on the key or push the button, and your meter doesn't show you what your SWR is because there's no power going out, your radio's not broken. It will not transmit until you modulate. So what you do is you go to CW or FM or
AM.
AM will give you the carrier. Yeah, you go to AM. So on sideband, there won't be nothing. And I don't know, when I first started, I thought I broke my radio. Disadvantage of FM compared to single sideband is that only 1 signal can be received at a time. That's funny because
Unless they're exactly the same amplitude coming into the
I don't know.
And then you'll get both.
I hear double, well, okay. So yeah, there's doubles, two guys are trying to go through the repeater, and it comes out garbage. Unless one of them's got a whole lot more power than the other one reaching the repeater, in which case it might do to the one guy. But disadvantage of FM compared to single sideband is that only one signal can be received at a time. Now, if you've got two guys in sideband talking, you may not be able to understand it, because they'll be stepping on each other, but you still receive both signals.
So Bruce, if you have somebody on lower sideband talking at the same frequency as somebody on
Upper sideband.
upper sideband, can you hear them both? I mean, would
Depends
would
on
the
how
upper
good your
people-
filters are, but if you're on lower sideband and he's on upper, you're using different parts of the spectrum.
So you wouldn't hear it, but would
Yeah,
someone
so-
else?
Somebody else
Should
could
two
hear him if they were
conversations be
on.
going on side by side, one lower,
Yeah,
one
they
upper?
could, but we have a convention that certain bands, we use lower sideband, and other bands we use upper sideband. You don't require to, but that's the convention, so, and if you're scrolling along and you hear a signal, and you can't make heads or tail out of it, try the other sideband, it might be on the other sideband. But
Yeah,
yes, you can have a conversation here and a conversation here, and that's why sideband gives us more opportunity to get some more signals into a given amount of bandwidth.
Yeah, there are operators that will operate on the opposite sideband from convention just to have a little more privacy.
We're not allowed to encrypt. We'll get into that in regulations. We can't encrypt our signals, but we can do things like that to make it harder for somebody to hear us. If they know what's going on, they can still hear you crystal clear. Like, it's one way to keep people from listening in on your signal. Okay, disadvantage of FM compared to single sideband is that only one signal can be received at a time. Frequency modulation or phase modulation are commonly used for VHF and UHF voice repeaters, and they can be done with the same technology inside the radio. Continuous wave modulation is the signal with the narrowest bandwidth. CW has the narrowest bandwidth. FM and PM are commonly used for voice repeaters in VHF and UHF. And the disadvantage of FM is that only one signal can be received at a time. Lots of yellow up there. Okay, frequency modulation. Instead of varying the amplitude, we vary the frequency in step with the information in the waveform. So you can see how the frequency is getting squished here and opened up here. That is the modulation, squished and open. And it tightens up and moves and opens up based on the modulation that you're inputting to the signal. Not yellow. FM signals are much more resistant to the effects of noise, but require more bandwidth. So it takes up more space on the spectrum. FM bandwidth for voice is between 10 and 15 kilohertz. So, but it's not yellow, so don't worry about it. What's the bandwidth on lower sideband and upper sideband?
3.
3 kilohertz.